All right, welcome everyone. This is Patrick Rebeschini from Oxford. What I'm about to present to you is joint work with Thomas Vascovicius and Varun Kanade. Thomas is a PhD student in the statistics department where I work co-supervised between myself and Varun in the CS department. And in fact, what I'm about to present to you today really sit at the intersection between statistics and CS. Let me begin by introducing the general setting of supervised learning in machine learning. So the input is given by n IID data samples coming in the form of pairs of feature vectors and label or response coming IID from an unknown distribution P. And once we define the notion of population risk, here parameterized by a certain parameter A, so the population risk is defined as the expected value over realization of a new data point coming from the same distribution P of a loss function, think of it as the square loss, that captures the deviation, the error between the prediction made by our function f parameterized by A with respect to the true response y. So if we define this notion of population risk, what we care about in machine learning is, well, the task of minimizing the excess risks, namely the deviation of the algorithm, the estimator A that we can compute, we can come up with as a function of the data, with respect to the best possible estimator in our function class. So what does it mean compute? What does it mean for the excess risk to be small? So there are well-defined notions of optimality. From a statistical point of view, a fruitful notion is given by the minimax notion of optimality. The best predictor function of our data, Z here is the pair of X and Y's, over the worst case possible distribution P in a family of distributions. And from a computational point of view, of course, the benchmark, what we would like to achieve is being able to compute an estimator in a time linear or quasi-linear with the size of the problem. If we have d n data points, each of them d-dimensional, this will be n times d. So today I will focus on how to achieve statistical optimalities in many settings of interest, and I'll point you to related work that also deals with computational optimality for the class of models I'm about to define. But so first of all, our goal is that of minimizing the population risk, as I mentioned, but because we don't know the distribution behind the scene, and we only have access to the data, a meaningful approach that permeates much of machine learning is that of looking at the empirical risk, which is a Monte Carlo and empirical approximation of the population risk. But we don't really want to minimize this quantity in general. Why? Well, because we are dealing with a finite number of data points. So if n, the number of data points, were to go to infinity by the large number, there would be no difference between empirical risk and population risk, but in general, we need to take that difference into account. And generally, there are two main paradigms to take this discrepancy into account if we focus on minimizing some notion of empirical risk. The classical way is that of choosing a subset of parameters, class A, and minimizing the empirical risk in this subset. In this side of the world, statistics and computation decouple. Statistics tells you which set script A to look at, and then there is the question of, well, okay, given this set, let's solve the empirical risk within this set. And the modern way, on the other hand, to approach this problem is that of merging statistics and computation, and namely treating solvers, iteratives, gradient descent-based method typically, as statistical devices, namely a sequence of estimators given by a function of times. And in this setting, all the parameters of the solvers, namely starting point, stopping time, choice of the learning rate, are seen to have an impact, an implicit regularization impact in terms of getting as close as possible to the minimizer of population risk, here represented by A star. So as close as possible, again, minimax away from it. And in this setting, the optimal choice of stopping time is a clear, again, tunable parameter that has direct statistical consequences. So very quickly, let me review what explicit regularization is about. And this is the main, one of the main inequalities typically used in the explicit regularization domain. so we break the excess risk that we aim to minimize as a function of three terms. The approximation terms is completely deterministic. It captures, well, what we lose by approximating, by focusing on a certain script A. Then there is the computation term, which is purely for a given realization of the data an optimization question. And then we have this so-called the statistics term, or also generalization term, which captures the deviation uniformly over the choice of parameters, say, in our set, the deviation from the population risk, small r, and the empirical risk. So this main decomposition, there are other in the literature, has been extensively investigated over the past decades, and has led to a rich theory that really sprang out from notion of statistical complexity, in particular notion of Rademacher complexity, which is a way to capture how complex a class of function is, how well, or namely how well it can fit random IID Rademacher data, random noise. And this approach leads to a variety of techniques in probability theory and statistics that lead to bounds that decrease with the square root of n, which is the so-called slow rate in machine learning. And over the past decade, really, a lot of, or a bit more, a lot of effort has been gone into trying to improve the standard classical theory and try to develop improved notion of so-called localized complexity, such as the notion of offset Rademacher complexity proposed by Lian, Racklin, and Sridharan a couple of years ago, to lead to fast convergence rates. So namely to statistical rates that scale as 1 over n, not as 1 over square root of n. And this notion of complexity relies on the following so-called geometrical inequality. X here is the data matrix, and by D. And we will see this geometric inequality will play a role also for the theory of implicit regularization that we are going to develop. In fact, our main contribution will be to isolate and underpin and discover the fact that early stop mirror descent precisely is inherently linked with this notion of offset Rademacher complexity, at least in the case of the square loss and linear or kernel machine methods. So very quickly, well, there are limitations of these explicit regularization techniques. In modern over-parameterized setting, the empirical risk has multiple global minima, but the bounds above does not differentiate. Any global minima will give the same upper bounds for the empirical for the excess risk. From the computation point of view, if the problem is non-convex in general, we cannot drive the computation optimization error as close to zero as we would like. And then, well, there is an issue with the approximation term, namely, it is true that statistics tells us the optimal choice of parameter A in some setting of interest, and then we can compute the approximation error there. But in practice, well, this optimal choice of the script A depends on a known quantity of interest, such as the level of the noise. And for all these limitations, really, the novel approach is that of, well, precisely looking at what iterative methods used in practice do as far as their generalization performance. So what are the iterative methods we're going to focus on? Well, let me first tell you, this is a head-to-head comparison between explicit regularization and implicit regularization in a model of interest, namely rigid regression. And here we see, this is one of many papers that could cite in this respect, that there is a pretty neat and fundamental connection between these two approaches, at least in some cases, such as this one. And here we see the optimization path of rigid regression as a function of lambda, that's excess risk, and the optimization path of gradient flow as a function of iteration time. And we see that the two curve matches, not just the minimum is achieved the minimum success risk is of the same order. But in fact, at least in this example, this paper by Riley et al. Shows that there is a multiplicative factor, so that at any point in the scale of t versus 1 over lambda, the two curves are at most 1.6 factor away. So this is a pretty neat phenomenon that we aim to investigate further. We look at mirror descent. So this is a generalization of gradient descent methods that can be defined as minimizing at each time step, as the algorithm that at each time step minimizes a linear approximation, practice a proximity term given by this notion of Bregman divergence. This is not a distance, it's not symmetric. Still, it provides a notion of proximity. Mirror descent has been acquiring a lot of coverage over the past decades, and there is more and more research trying to uncover its properties, not just from an optimization point of view or online learning point of view, but also from a statistical point of view. There is a taxonomy or proper choice of Bregman divergence that works well and fit the local geometry well in a variety of problems of interest. And this is the main theorem that we are able to derive. It deals with implicit regularization of mirror descent. A sub 0 is our point of interest, the starting point, sorry. A star is the minimizer of the population risk, what we would like to compute. And the green ball is here, well, so-called ball, maybe not convex, defined in terms of these Bregman divergences. And the theorem that we are about to present claims that only its path towards converging to the minimizer, a minimizer of the empirical risk. The algorithm will stop, so there exists a stop in time function of the mirror map, the precision epsilon, and the starting point, such that at the stopping time we stay in this ball, and so all the way up to the stopping time we stay in this ball, and at the stopping time, the same geometrical condition that appears in the use of offset marker complexity holds up to precision epsilon. And so if we tune this epsilon to be the minimax rate, we do recover minimax optimality whenever this localized notion of Rademacher complexity is optimal. So this is our main theorem. I'll skip quickly. The main proof builds upon completing the convexity inequality and really dealing with an inequality at this level. The proof reads one slide. I didn't want to comment on this, but I just want to show how neat the picture is. We have numerical simulation for this. We have a preprint about this work. And as far as computational optimality is concerned, we have another related work that focuses on the lassos and shows how, in that particular case, implicit regularization gives both statistical optimality and computational optimality. Thank you.